Alright, last time we were working on modular arithmetic in the wonderful world of Z mod n. And just want to remind you of some notation and things like that before we move on into section 2.3. In Zn, for the algebraic structure of Z mod n, we talked about this circle dot being multiplication and the circle plus is the addition. So A circle dot B, equivalence class A times equivalence class B. What you're supposed to do, that's equal to just basically take A times B and make it an equivalence class. And for equivalence class A plus equivalence class B, you take equivalence class A plus B. But honestly, writing these little circle pluses and circle times gets kind of old. So, mathematicians are inherently lazy. So after a while, we drop the little circles, and we just know this is in the wonderful world of Z mod n. And so we would end up basically just writing it like this. Equivalence class A times equivalence class B, that's equal to equivalence class A times B. Now, remember, this is not the exact same multiplication. For example, if I'm in like Z4, and in Z4, 2 equivalence class 2 times equivalence class 4, let's try this, equivalence class 2 times equivalence class 3, and Z4 would be equivalence class 6. But 6 is too big. Z4 is actually 0, 1, 2, 3. So I got to convert 6 back into Z4, and so 6, basically, you divide by 4 or keep subtracting 4, you get 2. So you end up getting 2 times 3 is equal to 2 type of thing here. That's the idea of the multiplication within the equivalence class. So basically, we're dropping the circle times and the circle plus, and just understand this is in Z mod n. So to multiply equivalence classes, you just multiply the numbers and make an equivalence class. To add equivalence classes, you just add the numbers and then make it an equivalence class. Some other notation on this particular material is the concept of exponents. We are doing algebra with this particular material. And so the idea of equivalence class A raised to the P power. Now, P is not part of Zn. It's just telling you how many terms of A you're going to multiply. So A, equivalence class A to the power P is equivalence class A times A times A dot 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 times A, P times. You've got P equivalence classes being multiplied here. Okay, so this is just a number. And so, for an example here, in Z5, if I've got equivalence class 2 squared, that means it's equivalence class 3 squared. That's equivalence class 3 times equivalence class 3. Now, 3 times 3 is 9, but in Z5, 9 is equivalent to 4. So, wonderful math here. 3 times 3 is equal to 4 in equivalence classes, mod 5. Now, here's another example. In Z mod 3, remember in Z mod 3, you're allowed to have 0, 1s, and 2s. So 2 raised to the 4th power. Now notice 4 is not in Z3, but this is not supposed to be a part of Z3. It's just the exponent telling you how many terms you're going to multiply. So equivalence class 2 to the 4th power is 2 times 2 times 2 times 2, which officially is equivalence class 16. But in Z mod 3, when you take 16 and divide by 3, you get a remainder of 1. So it's equal to the equivalence class 1. So notice, a little side note here, these powers are not inside your equivalence class. So 2 to the 4th is not the same thing typically as 2 to the 1st power. Even though in Z3, 4 is equivalent to 1, that's not how this game works. These are just powers telling you how many copies of your base that you're going to have being multiplied together. So it's classic exponential notation in the wonderful world of Zn. So moving on to section 2.3, Z mod P, where P is prime. Now this is going to be a very special case when you mod out by a prime integer. Okay. So Theorem 2.8 says this: if P is greater than 1 is an integer, then the following are equivalent. And that classic notation for then the following are equivalent math, again, that inherently lazy concept here, we would abbreviate that as TFAE. The following are equivalent. So if you've got 1, you've got all these guys. So let's take a look at this. 1, P is prime. 2, for any equivalence class A not equal to 0 in ZP, the equation AX equals 1 has a solution in Z mod P. So we can solve this guy. Now, if you look at this concept, A times X is equal to the equivalence class 1. When you solve for X, in algebra, if it was like real numbers or whatever, X would be equal to 1 over A. Well, I don't know about division or anything like that, but we do call this the inverse of A, because 1 is the multiplicative identity for any Z mod N, and especially Z mod P. So A has a multiplicative inverse. That's basically the English behind what I'm trying to tell you with part 2. And part 3 says this: whenever you have B times C is equal to 0 in ZP, then either B is equal to the 0 equivalence class or C is equal to the 0 equivalence class. Now, traditionally, in Z mod N, that won't work. For example, in Z mod 6, 2 times 3, equivalence class 2, times equivalence class 3 is equal to equivalence class 0. Two non-zero elements multiplied together give you 0. But when you have Z mod P, that won't happen. If you got the product of two guys equal to 0, when you're modding up by a prime, that will go back and imply that either the first term was 0 or the second term is 0. And so if you got just one of these statements, if you got this situation for all elements of equivalence classes in ZP, automatically P is going to be prime. If I have that every element in the equivalence class Z mod P, that's not 0, by the way, has a multiplicative inverse, you can solve the equation A times X equals 1. There exists an equivalence class X equals, then automatically P had to be prime. So, and continuing on, we have Theorem 2.9. 2.9 goes back and looks at this equation. Now, we were first focusing on this one with P being prime. Now, take a look at Theorem 2.9. Let A and N be integers, with N being greater than 1. Then the equation, equivalence class A times X equals 1, has a solution in Zn if and only if the GCD of A and N is equal to 1 in Z. These, we're talking about the integers here. A and N, but for the GCD to be equal to 1, we're talking about A and N are relatively prime. So it's a relationship between the coefficient in front of the X and the mod number N. And if that relationship is the GCD of A, the coefficient in front of the X, and N, the mod number, is 1, you're going to be able to have a solution to this equation. AX equals 1, and that X represents that multiplicative inverse of A. But that multiplicative inverse has a, that's more of an algebraic thing from high school, so we got to give it a fancy name. So I got a couple of definitions down here for you. An element A in Zn is called a unit if the equation A times X equals 1 has a solution. And just a note, that X that you're trying to solve for is really going to be this A with a little minus 1, and that little minus 1 is referring to classic algebra notation of inverse, the inverse of equivalence class A. So this is called a unit. We don't typically call it the multiplicative inverse, too many words. We call it a unit. If an element has a unit, it has a multiplicative inverse. You're going to be able to solve this equation. A times X equals 1, and you can find an X that solves this equation. And that X really is that multiplicative inverse. But we also have one other definition here, and it goes back to that idea of two guys multiplied together equals 0. Now, a non-zero element A of Zn is called a zero divisor if the equation A times X equals 0 has a non-zero solution. So an element, pointing bracket A, of Zn is called a zero divisor if there exists another element in Zn that when I multiply them together, that gives me 0. Now both of them have to be non-zero because your trivial zero divisor is always 0. 0 times anybody is 0. But we're talking about non-zero elements here. So you've got a non-zero element times another non-zero element equals 0. So for example, back to that Z6 example I gave you. In Z6, equivalence class 2 times equivalence class 3 is equal to 0. So 2 is not 0 and 3 is not 0, but their product is 0. That means equivalence class 2 and equivalence class 3 are zero divisors in Z6. So we have another theorem here. Theorem 2.10. And 2.10 again goes back to, and it's just tying the last theorem together, just to remind you of the theorem 2.9. It's a restatement of theorem 2.9, but we're going to get rid of this idea of the equation ax equals 1 has a solution. When it has a solution, that solution is called a unit. So they basically just rewrote in your textbook theorem 2.9 using the words. So theorem 2.10 says this: let a and n be integers with n being greater than 1. Then equivalence class A is a unit in Zn if and only if the GCD of A and n is equal to 1 and the integers is Z. So if you're looking at the relationship between the equivalence class number A and your mod number n, and when they are relatively prime, that equivalence class A will always be a unit. It will always have a multiplicative inverse within the set. Now another theorem, and applying with this and talking about more algebraic structures, is this guy here. Now, let P be a positive prime integer. So P is going to be prime, and it's got to be a positive prime because it's going to mod out by it. And you can only mod out by positive integers here. So let P be a positive prime integer. Then for any A, equivalence class A, that is not equal to the 0 equivalence class, and equivalence class B in ZP, the equation AX equals B has a unique solution in ZP. And I'm focusing on this concept of the words unique solution. Okay? So we're going to prove this one because this is a classic proof in the concept of abstract algebra of existence and uniqueness. We're asking, or I guess you're trying to show that you have a unique solution. That word unique solution actually implies two things. You have a solution, so the existence of a solution, and this idea of uniqueness, one and only one solution. So how do I end up proving that? So to be able to prove a unique solution, you've got to prove two things: existence and uniqueness. So the first thing I'm going to focus on here is existence. Okay? So this is the idea of existence. All right. Given equivalence class A is an element of Z mod P, where P was prime. All of that was stated up here in the givens. Okay? Then, by theorem, and I'll go back and quote the theorem 2.8 because I want the equation out of it. By theorem 2.8, we know that the equation equivalence class A times X equals 1 has a solution. Now, since it has a solution, let's declare who he's going to be. So I'm going to let equivalence class U be an element of ZP such that this U is the solution, to be the solution of AX equals 1, such that equivalence class A times equivalence class U is actually equal to equivalence class 1. It's the solution, X equals U. Okay? Now, but remember, I am trying to show the existence of a solution to this equation, equivalence class A times X equals B. So as equivalence class A times x is equal to 1. Okay, u, put the u in there, equals class u is equal to 1. Then I'm going to multiply, here's your classic trick, multiply equivalence class b on both sides. Now if I did that, this would imply, thus, equivalence class A times equivalence class U times equivalence class B would be equal to equivalence class 1 times equivalence class B. By the associative property, just going to throw some parentheses in there, we have equivalence class A times parentheses equivalence class U times equivalence class B is equal to, and 1 times B is equal to equivalence class B. So all I did was throw some parentheses in there, and that's called the associativity property. So as the equation is, let's go back up here, equivalence class A times x equals equivalence class B, and with equivalence class A times equivalence class U times B is equal to equivalence class B implies x has got to be equal to equivalence class U times equivalence class B, which by definition is equivalence class U times B. And that is the existence of a solution. This is the guy that works my equation. Now, the second part to this unique solution, we have the solution existence, we want to talk about uniqueness. Now, how do you show uniqueness from an algebraic proof perspective? Well, pretty much, if there's a unique solution, there's only going to be one solution. So, assume you have two solutions, and watch. They'll end up being equal to each other. So, okay. So, as equivalence class A times equivalence class U times B is equal to equivalence class B. Okay. Making x equal to equivalence class U times B a solution. Okay, so I'm just restating what we basically had up here. And now I'm going to let, well, let's suppose that equivalence class W is another solution to equivalence class A times x equals equivalence class B. Okay. I.e., equivalence class A times W is also equal to equivalence class B. What I want to show is W is equal to UB. That's going to give me the uniqueness. I've got two solutions to this equation. Okay, so that's basically what I'm setting myself up here. Okay. So here comes the algebra. Therefore, equivalence class A times equivalent class UB minus equivalence class A times equivalence class W would be equal to the zero equivalence class, whether A times UB equals B and A times W equals B. So if I subtract A times UB minus A times W, that's the same thing as B minus B, and B minus B would be 0. Hence, equivalence class A times parentheses equivalence class UB minus equivalence class W, close parentheses equals to 0, and this is by factoring. Also, if you wanted to be fancy about it, factoring is actually the distributive property. But as U was the multiplicative inverse of A times U is equal to 1, then U times A times UB minus W is equal to U times 0. And what I did was, by multiplying U on both sides. Okay. Now, I'll slide this up because I'm going to need an extra sheet of paper on this one. So let me go in here and fill myself another sheet of paper. Some running out of room. Thought I could make it. No worries. So I'm going to slide this guy up a little bit. And then here we go. I multiplied by U on both sides. But as A times U, which is also equal to U times A, because in Z mod P we have commutativity. It doesn't matter what order you have these guys in. But remember, A times U was equal to 1 from our theorem 2.8. That was equal to 1. Hence, 1 times U times B minus equivalence class W is equal to, and U, equivalence class U times equivalence class 0 is going to be 0 by substitution. Okay, so to let you know what's going on here, I substituted in for U times A, that was equal to 1, and substituted in for U times 0 is 0. And equivalence class 1 times any equivalence class is always the other equivalence class. Thus, equivalence class U times B minus equivalence class W is going to be equal to 0, implying, I'm just going to add W to both sides, that I'm going to get the equivalence class UB is equal to equivalence class W. Therefore, X, which is equal to equivalence class UB, is the unique solution to the equation AX equals B. And we're done. Again, just to emphasize this, from the original existence, I have a solution, which was UB. And then to show uniqueness, I suppose I have another solution. I call him W. And then I plug both of these two guys into the equation and subtract them. And at the end of the day, I end up showing you that equivalence class UB is actually equal to equivalence class W. So assume we had a second solution, but the fact is the second solution is the same as the first solution, which means that's uniqueness. So this is a great example of showing you how to show a unique solution. You've got to first show there's a solution, and then to show uniqueness, you assume there are two of them, and then to show they're equal to each other. That's how you prove uniqueness in a particular proof. So the next theorem, is a theorem to actually help you out with solving these interesting equations that you end up running across. So look at this theorem. This theorem states this. Let A, B, and N be integers with N being greater than 1. And let D be equal to the GCD of A and N. Okay, and look what I'm going to set up here. N is going to be my modulo number, what we're going to be modding out by. And A is going to be the coefficient in front of the x. Look what happens. The equation AX equals B, equivalence class A times X equals equivalence class B, has a solution in Zn. Now, N does not necessarily prime here. If and only if D divides B. The GCD of A and N has to divide what A times X equals. So when the GCD of the coefficient in front of the X and the mod number divides what it's equal to, you're always going to get a solution on these guys. Now, what does it mean to have a solution? Well, you can have a unique solution, or you can have a not unique solution, which means you can have multiple answers. So you're going to get a solution. It's going to may be just one solution, or you may have multiple solutions with this. Number 2 says this. If D, which is, remember, is that GCD of the variable in front of the X, the coefficient in front of the X, and the mod number, D. If that GCD of the coefficient in front of the X and the mod number, D, divides B, then equivalence class A times X equals B actually has D distinct solutions in Zn. Actually, this is telling you how many solutions you're going to get, and it's basically what the GCD is. So if the coefficient in front of the X and the mod number is relatively prime, you're only going to get one solution for this guy. But if it's not relatively prime, if it's the GCD of the leading coefficient in front of the X and the mod number is like 3, you'll end up getting 3 solutions to this particular equation. So it's the relationship of the the coefficient in front of the X and the mod number and how it divides into B. It is basically going to tell you how many solutions you're going to have, if you have any solutions at all. So this is kind of an important theorem to basically help you out with being able to solve these algebraic Z-mod N equations. So speaking of that, I decided I wanted to give you some examples of equations that you're going to be solving. In this case, I put the Z-mod in. So I wrote up 3 equations on this guy down here. Okay? So, in Z8, I chose 8, so N is going to be 8 in my example here. In Z mod 8, solve the equations. 2x plus 7 equals 1. And then solve the equation. Equivalence class 4x plus equivalence class 5 equals equivalence class 3. And the last one, equivalence class 3x plus equivalence class 2 is equal to equivalence class 7. So remind yourself, in Z8, you're allowed to have the equivalence class 0 through n minus 1. That would be 0 through 7. So you notice all my equivalence classes are numbers between 0 and 7 on this guy. Now, honestly, if you want to be able to solve this guy, the addition table with the tables that we did are actually pretty easy, you can do in your head. But once you get to the bigger mod numbers like 8, 9, 95, whatever it happens to be, the multiplication table is actually going to be very advantageous. So, to save myself lots of time on the video, I went ahead and wrote out for you the multiplication table in Z mod 8, just the multiplication table. Now, of course, these are equivalence classes, so on the top and on the left side, I put my little pointing brackets in here, but when I multiplied this stuff out, I didn't put pointing brackets because it was just basically wasting my ink here, but I understood these are pointing brackets in here. Now, so if I make you do one of these guys on the test, I really do expect you guys to put the little pointing brackets on there. But for our example, to be able to manipulate these guys, I'm not going to force myself to put the little pointy brackets around them to remind myself yes, they're all equivalence classes. And so just remind yourself something like 3 times 4 is equal to 4 in Z mod 8. Now 3 times 4 we know is 12, but in mod 8 you can either divide by 8 or subtract 8. And when you take 12 and divide by 8, the remainder is 4. And if I just take 12 and subtract 8, you're left over with 4. You're trying to get a number between 0 and 7. So this is basically what I did to get my table of this guy. But the multiplication table is going to be very advantageous. Let me show you. So for this first equation up here in Z8, I have equivalence class 2 plus equivalence class 7 is equal to equivalence class 1. I want to solve for x. Well, I'm going to do classic algebra here. I'm going to subtract equivalence class 7 from both sides. What I do to one side, I do to the other. So this would leave me with equivalence class 2 times x equals, because that would have canceled, and 1 minus 7 is officially negative 6. But equivalence class negative 6 is not allowed. You've got to have a number between 0 and 7. So to turn negative 6 back into that Z mod 8, I'm just going to add 8 to them. So that gives me equivalence class 2 times x is equal to negative 6 plus 8 is 2. So this ends up becoming my equation after manipulating it around and getting the 2x by himself. But now, take a look at your multiplication table for Z mod 8 under 2. 2 times what equals 2? Well, clearly 2 times 1 equals 2, so x is equal to 1. But wait, there's another one. In terms of my Z tables here, the Z mod 8 tables, 2 times 5 is equal to 2. 2 times 5 is 10, but in Z8, subtract off 8, you get 2. So you get another answer, and it is 5. So there are 2 solutions. So you get multiple solutions on this one. But with 2, coefficient 2, the only way you get 2 back again, there are actually 2 ways on coefficient 2. Now going back to that theorem that we were just discussing about the idea of the GCD of the mod number with the leading coefficient and the b, let's take a look at that guy. You had to get the equation as ax equals b. Look here. 2 is the leading coefficient in front of the x. That's your a. Your n is 8. What's the GCD of 2 and 8? It's 2. And since that GCD 2 divides 2, that tells me the GCD being 2 is going to give me 2 solutions. Now, if the GCD doesn't divide the b number over here, then the answer is going to be no solutions. But 2 does divide 2, so the GCD itself tells you the number of solutions you're going to get. That's what the theorem tells you. So let's do another one. Let's slide this up because I want my table down here again. So here comes your next problem, still in Z mod 8. Equivalence class 4 times x plus equivalence class 5 is equal to equivalence class 3. I'm going to subtract equivalence class 5 from both sides because I'm trying to solve for x. That leaves me with equivalence class 4 times x is equal to, now 3 minus 5 is equal to negative 2. But negative 2 is not allowed as an equivalence class. So, converting this guy over, just putting my little arrow there, this would mean that the equivalence class 4 times x is equal to, now equivalence class 2, and again we're in Z8, so equivalence class 2, I'll basically I'm going to add 8, negative 2 is equal to negative 2 plus 8 is 6. So this equation now turns into 4 times x equals 6. But they're equivalence classes because we're in Z8. Now, in the good old days of algebra in elementary school there, what you want to do here to solve for x is divide by 4 on both sides. You want to get the x by himself, play the game. The problem with algebra, in the modern algebra, you can add, subtract, and multiply, but you can't divide, because you can't guarantee you're going to continue to be in your same numbering system. So there is no division by 4 here, but I do have my multiplication table here. So when I sit down here and go x is equal to, and pretty much fill in the blank here, and my leading coefficient is 4, so I'm going to go to my Z8 multiplication table. I'm going to look down the line for 4, and I'm going to see when I'm going to get 6 and see what the answer is. Problem is 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 0, 4 times 3 is 4, 4 times 4 is 0, 4 times 5 is 4, 4 times 6 is 0, 4 times 7 is 4. I don't care what I multiply by, I never get 6. So since 6 doesn't show up, the answer is D and E. D and E is my code for does not exist. Another word for does not exist is no solution. So here's an example of no solution. So if I go back to my theorem that we just discussed, my leading coefficient is 4. We are in the wonderful world of Z mod 8. So the GCD of 4 and 8, the GCD of 4 and 8 is 4. So that's my D number 4. But the equation is 4x equals 6. So the B part is 6. And 4 does not divide 6 is why the answer is no solution. And that follows from the theorem. So let's look at this one right here. Again, remaining in Z mod 8. Equivalence class 3 times x plus equivalence class 2 is equal to equivalence class 7. I'm going to solve for x by subtracting equivalence class 2 from both sides. So get my equivalence class 3 times x by himself. And that's equal to 7 minus 2 is 5. Now I'm going to solve for x by going and looking at my multiplication table. So 3 times what is equal to 5? So I go down here to 3 and I look at 3 times what is equal to 5. So I go through my table and I see it over here. There's my 5. 3 times 7 equals 5. Well, this is in Z8. 3 times 7 is obviously 21, but in Z8, okay, basically you're going to take 21 and divide by 8, and you're going to get a remainder of 5. You could also do this. 3 times 7 is 21. Subtract 8, so if you subtract 16 from 21, you're left with 5. So the answer that I need to multiply 3 by to get that 5 is actually 7. And there's only one answer that gives me that. But again, going back to the theorem, we're in the wonderful world of Z mod 8. So my n is equal to 8. My coefficient in front of the x is 3, and the GCD of 3 and 8 is 1 because they're relatively prime. And when you have relatively prime between your leading coefficient and the mod number, your D equals 1. 1 divides everybody, and there's only going to be one answer. There's only one answer. So this is your unique solution situation. So when I go back and look at these guys on this particular one, I actually gave you an example of multiple solutions, no solution, and one unique solution. So when it comes to the algebra in Z mod n, you can have multiple different kinds of answers. Multiple answers, no answer at all, no solution, or unique solutions. So how bad can this stuff be? Well, I left you with one more example on this one. So I want you to solve this guy here. Now, solve for x, but I'm changing the world now, in Z mod 95. Now, the world's worst thing that I want to do is I want to do a multiplication table with Z mod 95. Z mod 95 is 0 through 94 equivalence classes. That's just way too large. Now, I can use some kind of computer-generated system to do this, but I'm not going to write this stuff by hand. We should be able to figure out what's going on here. And this one, I'll have to admit to you, I'm going to use a trick. Now, I've already got this AX equals B, and my mod number is 95. So, and here's the trick. The thing you need to know, the leading coefficient number, A, is 24, and the mod number N is 95. And the first thing I'm going to look at is when I'm trying to solve these equations is, what's the relationship between the two? What's the GCD? And what you need to know is that the GCD of 24 and 95 happens to be equal to 1. They are relatively prime. So that's a big note. That right there tells me because the leading coefficient of the x and the mod number are relatively prime, GCD is 1. I know there's going to be one solution to this guy. Now I've got to go find him. Now remember, because of this, from Theorem, and you're going to start memorizing these numbers here, 1.2 says that there exists, since the GCD of 24 and 95 is equal to 1, there exists integers u and v such that 24 times u plus 95 times v is equal to 1. Now, in these u and v, remember, they were not necessarily unique. So I'm pulling some old stuff as we continue to add on material to this guy. So Theorem 1.2, when I got a GCD, I know I can write an equation off of GCD. And this is going to be the trick. Now, you need to go and find the u and v on this guy, and I'm going to help you out with that one, but you're going to have to find those. But if you let, running it over here, if I let basically the u part be equal to 4 and the v part be equal to -1, it actually works. You get 24 times 4 plus 95 times -1. That actually equals 1. So there's more examples of u's and v's. They're not necessarily unique, but u is 4 and v is -1 actually works this thing. Here comes the trick. So remember the question. I want to know what I need to multiply by 24 to be able to get 5 and z mod 95. Use this equation. But you don't want the thing to be equal to 1, you want it to be equal to 5. So here comes the trick. Multiply by 5 on both sides. So you end up getting 24 times 4 plus 95 times -1. That whole thing multiplied by 5 is equal to 1 times 5. What I do to one side, I do to the other. Multiply both sides by 5. And I'm going to distribute the 5 here. So this will give me 24 times 4 times 5 plus 95 times -1 times 5 is equal to, and 1 times 5 is equal to 5. Now this is just in the integers, z. Well, what I'm going to do here is I'm going to put these guys back in terms of equivalence classes. So let's convert it back to z mod 95. Z mod 95. So this would be equivalence class 24 times equivalence class 4 times equivalence class 5 plus equivalence class 95 times equivalence class -1 times equivalence class 5 is equal to equivalence class 5. All I did was put equivalence classes in all these guys, but now I'm back in 95. Now, some of these numbers are just way too big to be in Z mod 95. In Z mod 95, 95 is equivalent to the 0 equivalence class. So all that part goes away, and you end up getting your equation. 24 times, I'm going to go ahead and put these two guys together. 4 times 5 is equal to 20. Equals, because that Z mod 95 is 0, and 0 times anybody is 0, so that goes away. So it's equal to 5, which implies that my x, what times equivalence class 24 is equal to equivalence class 5, the answer is actually equivalence class 20. And I didn't actually have to use my multiplication tables and stuff. But with Z mod 7, Z mod 6, Z mod 8, multiplication table is so much easier to use. But once you get in like Z mod 95, you're going to have some special tricks. The key is those theorems and that GCD of the leading coefficient, which are mod number. That tells you the different types of solutions you're going to have. Well, this is the end of Chapter 2, and after this we'll move on to Chapter 3.